Hi everybody, I hope this video finds you well. In today's video, we're going to be starting into our discussion of how to perform descriptive statistics for quantitative data sets. So this is going to be sort of a change of pace from what we were doing in the last couple of videos, where we were focused on the descriptive statistics for categorical variables, talking about ways to sort of organize categorical variables and visualize categorical variables, as we'll be sort of changing gears and focusing on the other type of data, quantitative data. As we'll see, just by the simple fact that there's going to be sort of 4 videos dealing with quantitative variables as opposed to just 2 videos for categorical variables, there's a lot more to sort of do and say when working with quantitative data than there is with categorical data. And the reason for that is that simply when working with quantitative data, we have quantitative information, meaning numeric values where we can perform arithmetic and really bring the sort of full power of mathematics to help us analyze this sort of data. So we've got a couple things to begin with, sort of some attributes of a quantitative data set that we'd like to be able to sort of understand or describe. So when working with quantitative data, there are 3 main things that we sort of want to measure and understand. And the first couple of these sort of lecture videos about quantitative data is going to focus on how to analyze these 3 attributes. So these are the center of the data set, the spread or variability of the data set, and the shape of the data. So what do each of these actually mean? Well, for the center of a data set, what we mean is that we want to sort of measure the middle of the data set, or basically understand what does a typical value from that data set look like. For the spread or variability of a quantitative data set, what we basically want to understand is how spread out or how closely packed together are all the numbers that form that quantitative data set. And then finally, the shape of the data, which might be the hardest to understand, but we'll sort of learn how to analyze it based on visual displays of quantitative data. What it basically means is we want to understand how the data is distributed, and oftentimes we'll talk about what distribution does the data follow. What that basically means is that when we visualize the data, is there some sort of pattern that we can describe? So we'll be looking sort of for pattern or shapes in the data. Now you might ask yourself, why are these 3 things the things that are important when working with quantitative information? So let's do a little thought experiment to sort of help understand that a little bit better. Say you're looking into a potential field that maybe you want to go into once you have your degree, or maybe it's a field that you already are applying for jobs in and you're getting offers and you want to compare salary information. Well, probably the first thing we want to do when analyzing something like salary information for a particular field or for a particular job is understand what's the typical salary for people in that field. The typical salary is something where we could sort of say, that's my sort of baseline goal. I'd like to make as much as people typically do in that field. So what we're basically saying there is we want to understand the center of the data set. But of course, that's not the only piece of information we might want. We might find out that, say, the typical salary in the field we're looking into is $60,000. But there could be a lot of differences there. Maybe we're looking into a field where the typical salary is $60,000, but pretty much everybody makes either $58,000, $59,000, $60,000, $61,000, $62,000. In other words, there is very little spread or variability. In some ways, that could be a really good thing, because I guess we wouldn't have to worry about getting way underpaid compared to what most people make. But it also could be a little bit concerning, because it doesn't really sound like there's much potential to make more than what's typical, right? Because there's very little variability there. On the flip side, there could be a field where the typical salary is $60,000, but some people make as little as $30,000 or $40,000 in that field, while other people make as much as $80,000 or $90,000. Now that has the same sort of center, 60,000, but it has a lot more spread or variability. Now, again, that could be good or bad. It could be good because that means there's a potential to make a lot more money in that field, but it could also be bad because there's also potential to make a lot less money. So that hopefully explains why we want to understand the center and the spread or variability. What do we mean by this shape, though? And this is maybe the hardest to understand from a thought experiment standpoint, and will get easier as we get visualizations. But if you think about it, there might be some fields out there where almost everybody is sort of clustered at the low end, and there's a few rare exceptions where people make a tremendous amount of money in that field. In other words, we'll eventually call that a right-tailed distribution, basically meaning that most people are sort of clumped at the low end. That's what's typical. That's the vast majority of people who work in that profession sort of make the low end salary, but there's a few rare exceptions of people who make 3-4 times as much as everybody else. Or perhaps you're looking at a profession where most people are in the middle, and it's pretty rare for people to make a lot more than that or to make a lot less. We'll call that a Bell or normal distribution later on, basically meaning that most people are in the middle, and it's just as rare to be far above the middle as it is to be far below the middle. So all of that is about the shape of the data set. The last thing I want to mention here before we actually get into talking about the ways that we're going to measure these things is to make a sort of really important comment relating the difference between statistics and mathematics. What we're going to be seeing here is that for each of these things, the center, the spread, the shape, we're going to learn several different ways to measure each of these. So we're going to learn 2 ways of measuring the center, 3 ways of measuring the spread or variability, and 3 different visual displays that help us understand the shape. That means there isn't just one center or one measure of spread. Depending on the measure you use, you can get different information, and we'll learn that in certain situations, one measure might be preferred. In other situations, a different measure is preferred. But it's really important to understand that each of these are attributes, and there's no one single way to understand them. Instead, we just simply learn some statistical measures that help us give a better sense of each of these components. So, without further ado, let's go ahead and actually start talking about our first one. How do we measure the center of a data set? So, we're going to discuss in our class 2 ways of measuring the center of a quantitative data set. Again, it should go without saying, but all these things, center, variability, shape, all of these are concepts that apply to quantitative data. We don't use any of this terminology when talking about categorical things. It doesn't make any sense there because in categorical data, you have people or individuals in categories. You don't have numeric values. So again, anything that deals with center, variability, shape, any of these measures we're talking about exclusively is applied to quantitative information. Are these 2 measures that we're going to talk about the only ways to measure center? Absolutely not. If you continue on in studying statistics, or you study statistics in your particular field later on in your educational or professional career, you'll see that there are tons and tons of different ways of measuring the center. Some are modified versions of what we'll talk about, some are completely different. But for our class, we're going to narrow our approach to talking about 2 ways to measure the center of a data set. So, the first, which is perhaps the most famous, is called the mean or the average. Most people have encountered calculating the average of a set of numbers beforehand in their mathematical careers. Probably a lot of you, when I kept saying center over and over again, were thinking, why don't we just say average? Isn't that how we measure the center? Well, as you can see here, it is one way that we measure the center, but it is not the only way. That's why we have to be sort of careful here and say that the average is a measure of center. It's not the only way we measure the center. All right, so let's talk about how you calculate the average. In words, it is very simple to explain calculating the average. To calculate the average of a data set, all we do is add all the numbers together, all the values in that data set, and then we simply divide by the amount of data points. If you want to be a little fancier, you could say we divide by the sample size, because the sample size is how many data points we have. There is sort of a spiffy or clever notational way of writing this mathematically. So we can say mathematically that the average is equivalent to the sum of x sub I divided by n, where each x sub I, when you see that x with a subscript, that means each data point. This uppercase Greek sigma basically means sum up or add up all the data points. And then, of course, we know n is our notation for the sample size. So this is just a very fancy sort of mathematical way of saying add up all the numbers in your data set and divide by how many numbers we have. In terms of notation, sometimes we just write out in words average or mean. Keep in mind, mean and average, they're just 2 words for the exact same concept. However, just like we use n for sample size, we also do have variables or notation for the average. So we will be using the Greek letter mu when we're talking about the average of a population, and we will use the notation of x with a bar over it when we're talking about the average of a sample. Now you should keep in mind there is no computational difference here. So in other words, the way that we calculate a average of a population and the way that we calculate the average of a sample is exactly the same. add up all the data, divide by how many data points there are. We just use this as a notational difference to help a sort of reader or somebody who's looking at statistical analysis know, again, if we're talking about a population, everybody that we wanted to study, versus a sample, a subset of that population. So mu, that's our notation when we have a population. X bar, that's our notation when we're talking about the average of a sample. Last comment about averages is that the units for the average is the same as the units for the data. Meaning if you have a bunch of weights in pounds, where maybe each of these weights is how much somebody weighs in pounds, well, the average weight would also be in pounds. If you have a bunch of reaction times, maybe people take a reaction time and you measure their reaction time in milliseconds, the average reaction time would also be in milliseconds. So the same units for the data apply to the average. So the average or the mean is the first way we measure the center of a data set. It's a very, very popular one, and we will use it a lot in our class. There is, however, a second way of doing it that we should talk about as well. The second approach to measuring the center of a data set, which could give a different result, is called the median. To calculate the median of a data set, all we have to do is organize the numbers into ascending order, so you put them as they get larger and larger, and you literally find the middle number. Now, this does break down into two separate cases based on how much data you have. So, case one, if you have an odd amount of data, so you have 5 data points, 21 data points, 117 data points, some odd amount of data, then the median will literally be the number that is in the middle. So you will be able to locate, because there's an odd amount of data, one data point that is exactly in the middle once you've put it into ascending order, and that will be your median. Case 2 is a little trickier, not much, but a little trickier. If we have an even amount of data points, so like 4 data points, 20 data points, 100 data points, then the median, well, it won't actually land at a particular value. It'll actually land between the two middle numbers. Then what you will need to do is you will need to average those two middle numbers, add them together, and divide by 2 to get the median. Either way, regardless of whether or not you're in case 1 or case 2, the median basically measures the center by cutting the data directly in half. In other words, no matter what your data set looks like, 50% of your data will be below the median and 50% will be above the median. That's not true for the average. It's only guaranteed to be true for the median. Notationally, we don't distinguish between population median or sample median. We always just use a capital M to represent the median. Finally, the units for the median are the same as the units for the data. So again, if you're taking the median of a bunch of people's weights in pounds, the median weight would be in pounds. All right. Now, at the end of this video, once we've introduced the measures of center and the measures of spread, we'll do measures of shape and visual displays in a later video. But once we've had a chance to talk about the measures of center and talk about the measures of variability, we'll have a little discussion. There'll be a separate video showing you guys how to use your calculator's statistical features to calculate all these things. But for this video, we will go ahead and calculate those things by hand. And all I mean by hand is by actually using the sort of formula or writing it out. We'll still use the calculator to do the arithmetic. We never need to add up things in this class actually by hand, like doing long addition or anything like that. But for now, we will go ahead and calculate mean and median without using any of the statistical features of your calculator. But after this video and for the remainder of our course, we'll just be using the statistical features to handle everything. So let's get in and take a look at a couple examples. So let's suppose that we've got this data that represents salaries for employees at some company in thousands of dollars per year. So we've got these 5 data points. So the first person we talk to makes $42,000 per year. The second person, $77,000 per year, $49,000 per year, $90,000, $67,000. What we want to do is we want to calculate the mean and median of the sample, and we want to make sure to give units for these values. So let's go ahead and do this. So to start off with, we want to calculate the mean. Now we should notice that this is a sample. Now this is only 5 employees, which it's doubtful that it's everybody at the company, so we can assume that it's a sample. So if we go to do the mean here, notationally we would use X bar because it's only a sample. To do this, what we're going to do is we're going to, in the numerator, add up all these data points. So 42 plus 77 plus 49 plus 90 plus 67. And then we're going to divide by the amount of data points. We have 1, 2, 3, 4, 5 data points, so we'll divide by 5 here. All right, we can go ahead and use a calculator to just add up the numerator. So 42 plus 77 plus 49 plus 90 plus 67. We should get 325 up top. Does this 325 have any meaning? Well, if all these people pooled their salaries together, their total salary altogether is $325,000 per year. And then that's divided amongst those 5 employees. If we go ahead and do that division, we would get that that is equal to 65. What are the units? Well, it would be $65,000 per year. So what this tells us is that the average salary, according to our data, for people at this company is $65,000 per year. Notice that a couple people make less than that, the 42 and the 49, and 3 people make more than that, the 67, the 77, and the 90, right? But you can see how this sort of shows us one way of imagining the middle of this data set. Let's go ahead and get the median. It's tempting to say that the median is the middle, so it's right there, the 49, but keep in mind, if you have a random data set, you first need to put it in ascending order to get the median. So, in terms of ascending order, we have 42, then 49, then 67, 77, and 90. Visually, the median then would be located right here, where it would split the data in half, 2 points above, 2 points below. Half of the data here, half of the data here. So this would tell us that our median, M, equals 67, and again, units would be $1,000 per year. So notice, mean and median can very easily give you different values, but they both attempt to measure the middle of the data set. This is basically saying that an equal amount of people in our sample made more than 67,000, these 2 people, and an equal amount of people made less than 67,000, the 42 and the 49. So 2 different ways of measuring the center of this data set. At this point, aside from maybe just expanding our knowledge, we might be interested in why we need 2 separate measures. I mean, why do we have to have 2 different ways of measuring the center? So to help us understand that and to introduce a very important definition about statistical measures, let's continue this example and imagine that we added 1 extra person to our sample. So maybe we initially talked to these 5 people and collected this data, but maybe we add 1 more person. So let's suppose we interview that 1 additional person, and we still have this data that's in thousands of dollars per year. So there's our first 5, 42, 77, 49, 90, 67, the same 5 people. But then this 6th person announces to us that they make $225,000 per year. So very, very different from the rest of the data. Let's go ahead and calculate the mean and median again. Now, of course, we expect that the mean and median are going to change because we have new data. We have 1 new data point. But you should think a little bit about, before we do this, do we think that they're both going to change a lot? Is one of them going to change a lot and one of them isn't going to change a lot? How is this extra data point going to impact our mean and median? Well, let's start with the mean here. So the mean, it would still be X bar because it's still a sample. We'd still add them together. So 42, 77, 49, 90, and 67, and then plus the new one, 225. And of course, we would divide by something different now. Now we have 1, 2, 3, 4, 5, 6 individuals. So we would divide by 6. Once again, if we're doing it sort of by hand, we can go ahead and add up on our calculator the numerator, and we should get like 550 up top divided by 6. And if we do that, we should get that that's approximately 91.7. Doing a little rounding there. And that would be $1,000 per year. So we would now say that the mean is $91,700 per year. Okay, let's go ahead and get the median. For the median, we need to again put this in ascending order. So 42, 49, 42, 49, 67, 77, 90, and 225. Notice that the middle now, because we have an even amount of data, is right there, where 3 data points are here, 3 data points are here. So our median lands between these two. To actually calculate the median, we would then average these two numbers together. So the median would be 67 plus 77 divided by 2. 67 plus 77 is 144 over 2, which is 72. So this tells us that our median would be $72,000 per year. So what happened here? Well, if we go back and we can compare, well, what we can see is that the original mean was 65 and it jumped up to 91.7, while the original median was 67 and it increased up to 72. So, as it would make sense, adding this one person who happened to make a ton of money per year caused the mean and median to go up. But notice it caused the mean to go up by a lot. It went from 65 and it jumped by more than $20,000 up to 91.7. Whereas the median only increased by about 5,000. So what this tells us is that the mean is very sensitive to really extreme values, right? This 91.7, I mean, it is the correct mean, but is it really a typical salary anymore? Only one person is anywhere near that 91.7. A bunch of these people, the 42, the 77, the 49, the 67, are nowhere near the 91.7. Neither is the 225. Now, he's probably not mad that he's not near the average, but really, this average isn't that accurate or useful anymore because of this really extreme value. So this introduces us to a really important concept about statistical measures. This is what we reference in statistics as understanding the idea of resistance. So let's give a quick definition and then come back to this mean and median. So a statistical measure is said to be resistant if it is not greatly impacted by the presence of extreme values. What that previous example just showed you guys is that the mean is not a resistant measure of the center, while the median is a resistant measure of the center. And that is really why we want both of them, because we want to make sure we have a resistant measure of the center in case we have really extreme values, and if we don't have really extreme values, then we should be safe in using the mean. As you guys will see much later on in our class when we're doing statistical analysis for inferential statistics, oftentimes we will need to check a condition, because a lot of our inferential statistics is based around the mean, that there isn't any extreme values in our data set. Because as we just saw here, if there are extreme values, the mean can get very thrown off. So just keep in mind, resistance is a sort of term we apply to statistical measures. So far, we've seen that the mean is not resistant, the median is resistant. Okay, now that we've introduced these measures of center, we're going to talk a little bit about extending specifically the concept of median to talking a little bit about measuring positions in general in a data set. So we're going to have a quick sort of diversion. Normally we would go straight to the sort of measures of spread or variability, but I'd like to introduce this just real quick here. So we're going to talk briefly about what are called measures of position and sort of a famous thing called the 5-number summary for a data set. So as we saw, the mean and median are examples of measures of the center, which is sort of our main focus. However, sometimes there's this sort of nice structure off of the median that allows us to not just focus on the center, but focus on a couple other major positions in our data set. So we're going to talk about what are called the quartiles. So the quartiles are 3 values, Q1, Q2, and Q3, that cut our data into 4 equal pieces. Now this is always a little bit weird to think about 3 values cutting into 4 pieces, but if you think about that, you have sort of a line there. If you make 3 cuts, you get 1, 2, 3, 4 pieces. So if you have 3 cuts, you're going to get 4 pieces. And the 3 quartiles cut our data into 4 equal pieces. That's the key there. Specifically, if we give a definition here, the first quartile, Q1, is located so that 25% of the data is less than it and 75% of the data is greater than it. So in other words, it's right at the 25th percentile. The second quartile, Q2, is located so that 50% of the data is less than it and 50% of the data is greater than it. You should notice that the Q2 is just a fancy name for the median, because what is the median? It's the spot that cuts our data directly in half. So this Q2 is actually exactly the same as the median. And Q3 is located so that 75% of the data is less than it and 25% of the data is greater than it. So in other words, the third quartile, Q3, is right at the 75th percentile. So how do we actually find the quartiles? Well, again, after this video, there'll be a separate calculator video that shows you how to find the quartiles using your calculator, but it turns out it's not too bad to do by hand. As mentioned, Q2 is simply the median, which we know how to find. Put things in ascending order, find the middle. Q1 can then be thought about as the median of all the numbers less than the true median, while Q3 can be thought about as the median of all the numbers greater than the true median. How does that work? Well, consider this sort of visualization here. Say our data sort of is like represented by this number line. If we cut that number line in half, that's the median, also called Q2. Then, if we focus our attention just from the lowest number up to the median, if we cut that in half again, so in other words, if we find the median of just this stuff, well, that will be Q1. So if we then find the middle of the stuff lower than the median, that'll be Q1. And then if we do the same trick, we just focus our attention on everything above the median, we cut that in half, that will be Q3. So if we cut that right there, that'll be Q3. So in other words, if you want to find the quartiles by hand, you put the data into ascending order, find the middle for the median, then look at everything less than the median, cut that in half, that'll be Q1. Look at everything greater than the median, cut that in half, that'll be Q3. And then you'll have all three quartiles. Sometimes we like to put the quartiles together along with the minimum and maximum value. In other words, this value here, the minimum, and this value here, the maximum. And if we put all five of those numbers together, well, it gets the very aptly named 5-number summary of a data set. So if you ever are asked for the 5-number summary of a quantitative data set, that just means give the minimum, Q1, the median, Q3, and the maximum. All of these can be found using the statistical features of your calculator, but we will do at least one example where we just show how to do it by hand. As a quick side note, the units for all these numbers should be the same as the units for the data. So all of these have the same units as whatever your data actually is in. All right, let's go ahead and take a look at an example of this. So we're going to suppose that we have a data set that represents the heights in inches of a group of 10 adults. So we had somebody who is 72 inches, somebody who is 65 inches, 59 inches, 65 inches, so on and so forth. We're going to calculate the mean, and we're going to give the 5-number summary for this data set. And we're going to make sure to include units on all of this. So let's start with the mean. So for the mean, again, it would be a sample. So it's x bar is our notation. We're going to add together all of these data points. Again, later on, we'll be able to just feed this through our calculator, but just since this is our first time doing this, we'll add all those together, and we're going to divide by the amount of data. Notice we don't even need to count. It says that we have a group of 10 adults. So there we go. If we go ahead and add up that numerator, 72 plus 65 plus 59 plus 65 plus 61 plus 68 plus 68 again plus 67 plus 68 plus 78, we should get up top 671 divided by 10. And if we do that division, we get 67.1. So x bar here is 67.1 inches. So the average height here was 67.1 inches, or about 5'7.1 inches. Okay, let's go ahead and talk about the 5-number summary. For the 5-number summary, we'll need to put this data in ascending order. So it looks like the lowest data point is 59, then 61. If it helps, you can put little check marks as you use them. Then it looks like we have a couple 65s. So we'll write 65 and then 65. Then looks like we have a 67. Then 3 68s. Check, check, check. Then a 72. And then a 78. Okay, let's go ahead and find our median. So 1, 2, 3, 4, 5 data points. Our median should be right there. Notice that that means the median is 67 plus 68 divided by 2, which you should be able to type into your calculator and get 67.5. So our median is 67.5 inches. We'll summarize that in just a moment. How do we find the quartiles, Q1 and Q3? Well, for Q1, we're just going to focus our attention on this stuff here. Where's the middle? Well, it would be right there. So this tells us that Q1 is located right there. And if we want Q3, we'd look at all the stuff above the median, cut that in half, and there we go. So Q3 would be right there. Notice that once we have all of these, all 3 quartiles, we have an equal amount of data here, 2, 2, 2, and 2. It divides it into 4 equal pieces. All right, let's go ahead then and write out the 5-number summary. So the 5-number summary here, the minimum, well, what's the smallest data point? It's right there. So 59. Then Q1, which was 65. Then the median, which we found to be 67.5. Then Q3, which we found to be 68. And then the maximum, what was the largest data point? Well, it was right there. It was at 78. We want to make sure that we include units, and they all have the same units, so we can just put a big bracket there and put inches. So in our sample, the shortest person was 59 inches, the tallest person was 78 inches, and then this tells us the locations of the 25th percentile, the 50th percentile, and the 75th percentile. Okay, so again, if you ever see reference to the 5-number summary, you know it means these 5 numbers regarding a quantitative data set. All right, so at this point, we've talked about how to measure the center of a data set, as well as how to measure a couple other positions given by the quartiles. It turns out the quartiles are also helpful for what we do next, which is to talk about measures of spread and variability. So let's get into defining the 3 measures of variability for data sets. So, measures of spread and variability. We're going to discuss 3 of them for our class. Again, there are a whole range of techniques for measuring the variability in a quantitative data set, but for our class, we narrow it down to these 3 major ones. The first one, which is very simple, but it's worth mentioning, is called the range. The range of a data set is very simple. You calculate it by taking the maximum of your data set and subtracting the minimum. The range basically tells us how spread out the data is from its lowest value to its highest value. The units for the range are the same as the units for the data, and the range, obviously, is not a resistant measure of variability. Why is it not resistant? Well, the range is literally based on the most extreme values in your data set. So if you have incredibly large or incredibly small numbers compared to the rest of your data, that's going to impact your range a lot. So the range is considered not resistant. Is the range super useful? Well, it's very easy to calculate, but to be honest, in practice, it's not particularly useful. The reason is that it is based only on 2 points, the maximum and the minimum. That means if you had a data set that had thousands of pieces of information, the range only uses 2 of them, which seems sort of like a waste. But we mention it because it is the simplest way to understand variability. How large is the largest value? How small is the smallest value? How far apart are those? The second way, and this is going to be the one that we use the most throughout our class, is called the standard deviation. The standard deviation measures how spread out the data is from the average. So in other words, the standard deviation says, let's use the average as how we measure the center, and let's see how spread out everything is from that center. The way we calculate standard deviation changes depending on if we are calculating the standard deviation of a population or a sample. Now this is very weird because we saw that for like the mean, it doesn't matter. If you're taking the mean of a population, the mean of a sample, you do it the same way. That's not true for standard deviation. So in our class, we have to be very careful if we're calculating the standard deviation of a population versus the standard deviation of a sample. Most of the time, as you can imagine, in statistics, you are working with a sample. So if you are ever unsure if a question is asking you about sample or population standard deviation, you should probably guess sample, because statistics often is based on samples. So what's the difference in how we calculate them? Well, both population standard deviation and sample standard deviation have pretty complicated formulas. They involve measuring the data point to the mean, in other words, the difference between each data point and the mean, squaring that, summing them together, then dividing by the amount of data, and then square rooting the entire result. Standard deviation is a super complicated formula to have to do by hand. This will be something we exclusively use the statistical features of our calculator on. So we won't do any examples where we have to calculate standard deviation by hand, and it's not something you guys will be required to do. So why am I showing you the formulas? Mainly to make sure you understand the difference between population and sample standard deviation. You'll notice that in population standard deviation, the denominator is n, whereas in sample standard deviation, the denominator is n minus 1. This is a big difference. I'm going to jump ahead to this note here for why this is important. Because this denominator is always larger than this denominator, and remember, the larger the denominator of a fraction is, the smaller the fraction is, population standard deviation is always less than sample standard deviation. So this is the main note to take away from actually seeing these formulas. We have special notation, just like we've talked about. We'll use the Greek lowercase letter sigma, so a little sort of thing like that, if we're talking about the population standard deviation. And we'll use the lowercase letter s for sample standard deviation. Again, this just helps people sort of read and understand, are we talking about a standard deviation for an entire population, or are we talking about a standard deviation for a sample? You might wonder, why are these two things actually different? Why is it that the standard deviation for population and sample are a bit different? It's a little beyond the scope of our introductory class, but it basically relies on some concept called degrees of freedom. And the best explanation I can give right now, because we'll actually revisit it later in our class, is that it really depends on the amount of information you have. In a sample, we basically view the amount of information we have as one less than the actual amount of data. For the population, we don't need to do that because, remember, the population is literally everything. So the information we have is literally the information we have. And that's sort of a quick understanding of why these denominators are different there. The units for a standard deviation, despite the complexity of the formula, are the same units as the data. So if you have data, again, in inches, the standard deviation would also be in inches. Standard deviation, because it's based off the mean, is not a resistant measure of variability. So if there are extreme data points, the mean can get very skewed by those extreme data points, and that means the standard deviation can get very skewed by those extreme data points. All right. We've got one more measure of variability to talk about. Again, keep in mind for this standard deviation, we will do some examples of calculating it, but we're always going to be feeding the data through the calculator to have the calculator handle the standard deviation for us. So you don't need to worry about actually plugging into these formulas sort of manually. Let's talk about our third and final way of measuring variability. The third is called the interquartile range. So as you can imagine, this is based on those quartiles we just introduced. The IQR measures how spread out the middle 50% of your data is. The IQR is very simple to calculate. You calculate it by doing Q3 minus Q1. So you take the third quartile and you subtract the first quartile. The IQR has the same units as your data set. And the great thing about the IQR, the reason we discuss it, is that it is a resistant measure of variability. That's why we actually bother talking about this. The standard deviation is almost always what we're going to end up using as our measure of variability, but in situations where we're concerned about extreme values, we will see how to use the interquartile range. All right, so this sort of wraps up our introduction to working with quantitative variables. In the next video, you'll see a quick demonstration using the calculator to handle calculating all these different statistical measures, and then we'll get back to some examples of actually understanding what these different measures of center and spread are really talking about.